Welcome to the deep dive. Today we're diving into some really interesting source material you shared. It's about silicone.
Yeah, a material everyone thinks they know, right? Like inside and out.
Exactly. But this stuff, it kind of flips the script.
It really does. The core finding here is pretty remarkable. It basically challenges what we've, always thought about silicone's fundamental properties.
Right. Because everyone knows silicone is an insulator. Full stop. Blocks electricity, resists heat, super inert. That's why it's in, well, everything. Cookware, electronics.
Medical implants, seals.
Yeah.
Yeah. And that holds true for, most silicones we encounter day to day.
Right.
But this research, this breakthrough stuff from the University of Michigan, it's work led by Professor Richard Lane. It was a Zijing Zhang, they call her Jackie, as the lead author. And what they found is that a new form of silicone can actually act like a semiconductor.
Whoa, hang on. A semiconductor.
Yep.
So instead of blocking electricity, this stuff can actually conduct it under certain conditions.
That's the gist of it. It's a complete 180 from its usual job description.
That's wild.
It is. And it's not just a theory. This is published work, tangible results. It's in macromolecular rapid communications.
Right, I saw the reference. Funded by the NSF and a Thai research fund, too.
That's right. National Science Foundation and the Thailand National Science Research and Innovation Fund. So proper backing.
Okay, so for this deep dive, let's try and unpack this. Our mission, really, is to get how this is even possible, like down at the molecular level. And then why does it matter? What's the significance?
And the applications, yeah. What could we actually do with this?
Because we're shifting from thinking of silicone as just, rubbery, inert stuff
To something potentially much more active, more dynamic.
Okay, so how does it work? Where do we start?
The molecules.
Definitely. You gotta look at the backbone. Silicones are polymers, right? Long chains.
Okay.
And these chains are made of silicon and oxygen atoms alternating. Si-O.
Look at chain link fence, kind of. Sort of, yeah. And usually there are organic groups hanging off the silicon atoms. But the key is that si-O-si chain. Now, normally the electrons in those si-O-si bonds, they're pretty happy staying put. They don't move easily along the chain.
Which makes sense for an insulator. No electron flow, no electricity.
Exactly. For something to conduct, especially like a semiconductor, electrons need to be mobile. They need to be able to get energized, jump from their normal spot, their ground state, to a higher energy excited state.
Okay.
And once they're in that excited state, they can move along the material, carry a current.
So what's different about this silicone? How does it let the electrons make that jump?
It all comes down to the angle of that si-O-si bond. It's geometry, basically.
The angle.
Yeah. In your standard silicones, that angle is pretty tight, around 110 degrees. It's sort of kinked.
Okay.
And that kink means the electron orbitals, think of them as the clouds where electrons live around the atoms. They don't overlap much across that bond.
Like pinching a hose. Makes it hard for water to get through.
That's a decent analogy, yeah. Not much of a path. But in the specific material these Michigan researchers made, it's a copolymer, a mix of structures. They engineered it differently.
Wow.
They managed to get that si-O-si bond angle much wider. Even in its normal resting state, it's closer to 140 degrees.
Already wider.
Already wider. But here's the really cool part. When an electron does get excited, absorbs energy and jumps up,
Yeah.
that bond angle stretches even further, out to about 150 degrees.
So the chain literally straightens out a bit when it gets energized.
That's it. It stretches. And that wider angle, that 150 degrees, that changes the geometry just enough. Now, those electron orbitals on the silicon and oxygen can overlap significantly.
So that's the pathway.
Exactly. It creates a sort of bridge for electrons to hop across those si-O-si bonds. Professor Lorraine pointed out this interaction wasn't really expected, but it allows charge to move. And crucially, they found that if they make the polymer chains longer,
chain.
yeah, the longer the chain, the easier it gets for electrons to travel.
Right.
It takes less energy to do things like absorb and emit light.
Okay, so conductivity is unlocked by stretching that bond angle, letting orbitals overlap. And you mentioned light. That leads to the other amazing thing in the sources. This stuff has color.
Yes, and that's a huge deal for silicone. Standard silicones, they're clear, maybe white.
Right, they don't really interact with visible light much.
Exactly. But this new semiconducting version, it can absorb light because the electrons can now jump energy levels.
Absorb it, and you said emit it too. How does the emission part work?
Well, it's the flip side of absorption. An electron absorbs energy, say from a photon of light, and jumps up to that excited state.
Okay.
But it doesn't stay there forever. Eventually, it falls back down to its ground state.
And when it falls.
That has to release that extra energy it had.
Yeah.
And it often does that by spitting out another photon, another packet of light.
And the color of that emitted light depends on how far the electron fell.
Precisely. It depends on the energy difference, the energy gap between the ground state and the excited state.
Right.
And the researchers figured out they could control this gap
How?
by changing the length of those polymer chains we talked about.
Ah, okay. So chain length controls the energy gap.
You got it. Shorter chains mean a bigger energy gap. When the electron falls back down, it releases a higher energy photon.
Which looks bluer to us.
Bluer, yeah.
Yeah.
Higher energy light is towards the blue-violet end of the spectrum.
And longer chains.
Longer chains mean a smaller energy gap, smaller jump down, lower energy photon release.
Which looks redder?
Redder or orange or yellow, towards that end.
And they actually showed this, right? Separating out different chain lengths and getting a rainbow under UV light.
Yeah, it's a really elegant demonstration. You synthesize the mix, you separate it by size, and boom, different colors corresponding to different chain lengths.
That really drives home how controlling the structure at the molecular level, the chain length, the bond angle, directly engineers the material's properties, both electrical and optical.
It's beautiful material science, really, tweaking the fundamentals to get new behavior.
So let's talk potential. What does this discovery unlock? What kind of applications are Lane and Zhang thinking about?
Well, the big advantage here is flexibility, right?
Yeah.
Traditional silicon semiconductors, like in computer chips, are rigid, brittle even.
Sure.
But this semiconducting silicone is inherently soft, flexible, like regular silicon.
Okay, so flexible electronics is the obvious path.
Exactly. The sources talk about next-generation possibilities, things like displays you can bend or even roll up,
Wow.
wearable sensors that aren't bulky patches but are actually woven into your clothes.
Built right into the fabric.
Potentially, yeah. Or even smart fabrics that could, change color, display patterns, maybe simple information.
Clothing that lights up or changes pattern on demand. That sounds seriously futuristic.
It does feel like sci-fi, doesn't it? But this is the kind of fundamental material innovation that could actually make it happen. Like Zijing Zhang said, they're taking something everyone dismissed as electrically boring and giving it this whole new potential, a potential, as she put it, to power the next generation of soft, flexible electronics.
Cool. Okay, let's just recap the core idea then. This whole amazing possibility hinges on understanding and then manipulating that psi-o-psi bond angle, getting it wider than the usual 110 degrees up to 140 normally, and then stretching to 150 when excited.
That stretch is the key. It enables that orbital overlap.
Creating a path for charge to flow where there wasn't one before.
Exactly. It fundamentally changes what silicone can do.
Yeah.
It opens the door for those flexible electronics, the colorful materials, all the stuff the researchers are excited about.
It really makes you think, though.
Yeah.
I mean, they took silicone, a material we use everywhere, something we thought was completely understood, and just by looking really closely at its basic structure, those bond angles, how electrons behave, the chain lengths, they found this completely unexpected property.
It shows there can be hidden potential even in the most familiar things.
Totally. So it makes you wonder, doesn't it? If they could reimagine silicone like this, what other everyday materials might be out there just, holding secrets?
Waiting for someone to look at their fundamental structure in a slightly different way.
Yeah. What other surprises might be locked away in common stuff just waiting to be unlocked? And what kind of future tech could that enable? Makes you think.